Right. Hello, everyone. It's great to be here. It's great to be back at the Galaxy Workshop after so many years and being welcomed by a sunny, warm day in Santa Cruz. So I'm the last talk before dinner, so I'll try to keep it tight. I know you're all tired. I'm going to be talking about extremely red objects, just like the ones that Dale mentioned, this population of perhaps dusty galaxies or obscure AGN that seems to appear and has been discovered by JWST at redshift above 5. It all got started a whopping 2 weeks after the JWST data was released. Yves Labbé and collaborators published this paper finding these extremely red objects, high redshift, relatively massive, maybe not too much, but some of them relatively above the 10 to the 10 solar masses, so dangerously close to breaking some models. Since then, there's been a flurry of paper, 10 plus, and many more in preparation, following up these sources. That why the interest, right? So, of course, they could be massive galaxies, AGNs, high redshift. This is all exciting. And we do have an obsession for red compact sources. I know, dropouts. We all chase them. But I think there's more to this is because these sources are really puzzling. They're really weird, and we are all driven to these things because we need to explain what they are, and it's not an easy fit, right? It's not an easy puzzle to solve. We still need work to do after all these many papers. We're making progress, but we're still not sure what they are. And the second one is that they're quite abundant, right? So we're not talking about supermassive, very bright objects, quiescent galaxy at redshift 5. It's not a handful of them. It's like half a source per square arc minute. We have 40 in the Sears area. There are many more in other surveys. So when you make your UVJ diagrams, your star-forming main sequence, they are there, right? When you do these diagrams at high redshift, they are there, and you don't know where to put them. Are they massive galaxies? Are they again? What are they? They are in your diagrams. We need to understand them, and they are actually a little bit weird. So just give you an outline. I'm going to be talking about these galaxies. I'm going to talk about the selection that they have just outlined, and then we're going to focus a little bit on how can we model these sources, how can we make progress to understand what they are. Right, so here's the selection diagram. Avoiding fancy names, I decided to call these galaxies EROs because I think they fit a very classic criteria that you can select them with that color magnitude diagram. You don't need anything else, right? So magnitude, this is the 444 filter, so 277 minus 444. This is the relatively short baseline filter to make the cut here. So above 1.5, you select red objects. You can see that relatively faint magnitudes around 26 or so. Some of them are relatively brighter, and those are the ones that are potentially more problematic. But they give you a nice distribution over here. The different colors indicate the sources that are selected by this criteria, but they also have additional observations in the Sears survey that they'll just describe. They have either MIRI or NIRSpec follow-up spectroscopy. So one thing that I wanted to highlight from this diagram is that you use some of the other traditional ERO selection criteria, like based on the H-band, for example, so 160 or 150, so it's a longer baseline. We have been doing this for ages, right? So you select these other red galaxies over here that are typically above redshift of 3, massive, dusty, or quiescent galaxies, and you typically have a put a limit in the magnitude because if you go fainter, then you start mixing, due to the evolutionary track, you start mixing some low-mass galaxies, so the sample is not that clean. What I'm going to show you is that this selection, just 277 minus 444, above 1.5, selects these and only these weird galaxies above redshift of 5, and they're pretty unique. So if you replace this color magnitude by a color diagram, so same y-axis, but now you throw in another color, 150 minus 200, you can see that this galaxy is separate from the rest. Okay? And this track that you see here, this blob of galaxies, shows you the usual trend, right? So these are two colors, so when galaxies become redder in both colors, they're typically more massive, more dusty, quiescent, higher redshift. So this is the evolutionary track for more massive and dusty galaxies. What you would expect beyond redshift of 5 is that these galaxies are there, right? They continue the track, but they're not. They are simultaneously the reddest and the bluest galaxies in this diagram, which makes no sense, right? Or shouldn't make sense, right? There are ways that you can explain it. We'll go into that, but it's really weird. They are the bluest and the reddest at the same time. How is this happening? So let me remind you that above redshift of 5, this color here probes the optical. This color probes the res frame UV. So they are red in the optical, blue in the UV, which, again, makes no sense, right? If you have a very dusty galaxy or old galaxy, you're red in the optical, you're even redder in the UV, right? But they're not. They're very blue. So easiest explanation, we have been doing this even before JWST with the Spitzer. Why, if maybe these are some blue galaxies with a booming emission line, because you're just using this color. If a line gets into this filter, they're going to jump, right? They're going to follow up this plume that goes up all the way up here, and it could be just emission line contamination. This happened with the Spitzer observations. So let me throw in some evolutionary tracks here. So a galaxy, relatively blue galaxy, young galaxy with booming emission lines, if one of these lines gets into the 444 filter, you will get this shape where it's red in the optical but blue in the res frame UV because it's a blue galaxy, right? So it will jump up from redshift 4 or so, 5, 6, 7, so they will go all the way up here. But maybe not so red. So what we're thinking is that to go all the way up above this line, you need some emission lines, right? You can see the spike going up, but you also need a red continuum, right? And this is exactly Dale's source, the one that he showed you a second ago, where you have a red continuum and an emission line, and then both things boost you up, and then you cannot get all the way up here. But yes, you have a red continuum and a blue continuum at the same time. Okay, so that's the evolutionary track. You can jump up and get all the way up there. So the nice thing is that for Dale's galaxy, other than the beautiful high-resolution spectra, we have also the low-resolution spectrum that really show the continuum. So the continuum is there. It's not just emission line contamination. There is a red continuum in these sources, or at least in some of them. Right? There's another example from Mati, from the Grissom surveys, and we do see the continuum. Unfortunately, we don't have that many of these sources. I told you that we have 40 in Sears. This is one, and I think Mati finds something of the order of 4 or 5 in all of the goods north and south, where they should be finding like 60. So not all of them are going to be like this. It's not going to be a slam dunk. We're not going to be able to confirm all of them. What else can we do? So we can use additional photometry, and Caitlin already talked about MIRI and nice observations that we get in Sears and also Cosmos Web. So we can use additional observations at longer wavelengths, because if you do have an emission line in 444, you can go redder and try to probe a region that is devoid of emission lines. Unfortunately, all of our galaxies that have MIRI observations were detected. Unfortunately, all of them means 4, because as Dale just showed you, the MIRI coverage of the Sears fields is a little sparse, so we don't have coverage for all of them, but the ones that are observed are detected. Okay? And this confirms the continuum for these galaxies, because if I show you the stack SED, observe stack SED, these are all the filters. Here's MIRI. We only have 4 of them versus the multiple NIRSpec bands. All 4 of them indicate that the trend continues, right? The SED goes up. There is a continuum because the lines should be either in these filters or these filters, depending on if it's H-alpha, O3, depending on the redshift. So the purple is the stack for redshift 5-ish galaxies, and the red is the stack for the galaxies around redshift of 7. And again, the evolutionary track shows that these galaxies should be around redshift of 5 to 9, and we do have a continuum detection that suggests that the SED continues to go up. So other than that, they already hinted that, you can see that not only they are very red and weird in the LCD, they're also remarkably compact, right? This reminds us of the dusty star-forming galaxies or the red nuggets, the compact quiescent galaxies. But actually, if we do model their sizes and we try to put them in the mass-size relation, they're actually too compact. We can actually model these galaxies with just pure PSFs. We don't need anything else. They're actually essentially unresolved in all of the red NIRSpec bands and most of the blue bands. Also see this paper, Bagan et al., where they actually model this in a lot of detail, and they say they could maybe make up some sizes for some of the ones that are bluer in the short wavelength high resolution bands, but most of them are actually undetected. So we're not talking sub-kiloparsec, sub-half a kiloparsec. So they're really unresolved, which suggests that this might be more likely associated with a QSO than a galaxy. But again, it's not 100% conclusive. But all of the sizes strongly suggest that the galaxies are not resolved. All right, so let me jump into the second part, where we try to model this simultaneously red and blue SED. How can you do this? Well, you can try to model the population as a whole. It's going to be complicated, so you can use complex state-of-the-art models, different star formation histories, and dust emission and emission lines. And also you can model this with a galaxy plus strong AGN emission lines. But this is complicated because, as I mentioned, if the galaxy is very dusty, even if you have booming emission lines, the UV is always going to be more attenuated than the optical, because that's the way typical attenuation laws work. And typically, Calcetti attenuation law, the one that we use, attenuates the UV even more than the optical. So no matter how hard you try with stochastic, non-parametric star formation history, bursty star formation history, emission lines, you cannot do this, because then you are throwing it a lot of attenuation, because the AVs of these galaxies are around 3 to 4. You can maybe try to coerce the LCD to fit this a little bit better if you use more complex Charlotte-Fold or Crick and Conroy attenuation loss where you can actually essentially flatten the attenuation curve to make it completely flat so that the UV is not more attenuating than the optical, but it still is not a perfect job, right? So you can fit these galaxies, the optical, you can do a good job, MIRI, you can do a good job, the UV, it is really hard. So the next step is you can try to assume that these galaxies are made of two components, perhaps one of them is an AGN, and try to do this as a composite. Before that, let me show you some work by Ensley, Fortak, trying to model these galaxies with a galaxy and very strong AGN lines and a continuum from the AGN that will boost all of these filters, not just 444, and can also reproduce these characteristics safe. So it can be done with many different models. So we are still not sure. That's why we have so many papers trying to follow this up and convince ourselves that one solution is better than the others. So if we try a composite SED, right, to explain the blue and red SED that we see, you can use a quasar or a galaxy for the red part, but also a quasar or a galaxy for the blue part. You get all of these choices, so you have 4 possible combinations. Maybe the galaxy plus galaxy is not very likely because you don't seem to have a very large galaxy where you see 2 distinct components, one may be red, the other one may be blue. But you can certainly use a red plus blue quasar, as Dale just explained, so the scatter light will make up the blue component. You can use a quasar plus a blue galaxy host, or you can use a dusty galaxy and a blue quasar that maybe is just piercing through the dust and emerging from the very dusty galaxy. Long story short, you can do all these models with a lot of detail. The SED is not going to answer the question because they all fit the SED reasonably. You can tweak the emission lines to do a better job. You can change the attenuation a little bit better, but they're not significantly different. So for one galaxy versus the other, you can have subtleties, and essentially the SED is not going to distinguish between them. There is a chance that when you get better MIRI data, right, you can probe this region, and if you have a very dusty AGN, the SED is going to tend to continue going up, versus the dusty galaxies should have some sort of 1.6 micron bump, so the SED should go up and then down, and then you get the part where the dust emission rises. So they should be distinguishable around this regime where we don't have data yet, but in principle, with the data at hand, it's very difficult to distinguish all of these models that are all possible. So, of course, they are all possible, but they all have different implications, right? If you go for a red QSO plus a QSO or a blue galaxy for this other component, you have a continuum coming from a relatively bright quasar, so the luminosities are something of the order of 10 to the 45 to the 46, so they're borderline close to the regime of the blue quasars. Attenuations are pretty high, and the black hole mass that you can infer from these luminosities are something of the order of 10 to the 7, 10 to the 8. If you add a blue component that is a quasar, you get these mild UV luminosities, but again, this is supposedly coming from a scatter component, so it's not the intrinsic emission from the quasar, but rather some percentage of the light being scattered. And you don't have constraints on the mass of the host, because if this is the quasar and this is the quasar, you don't see the host, you don't know anything about the host, and it should be pretty massive, right? Because if this is the black hole mass that you have, the mass of the host should be also relatively high. If you fit this blue part with a galaxy, then you get masses something of the order of 10 to the 7, 10 to the 8. You can see that over here. So this is a galaxy, so mass is something of the order of 10 to the 7.58. So this is a galaxy instead of a blue quasar. And then you get some constraints on the mass of the host. And you can compare the mass of the host to the inferred black hole mass. And you see that it's dangerously close, so we're not very comfortable with that. They seem to be very luminous because of the high attenuation. Then if you go with the dusty galaxy to model the red part, so the dominant part of the SED is a dusty galaxy instead of an AGN. The problem is that some of them can be very massive. So not 10 to the 10, some of them, the brightest can get all the way up to 10 to the 10.7, which at redshift 5 is not too bad, but some of them can get this massive around redshift of 7. That was Ivo's problem in his first paper when he thought they were massive galaxies. And then you can throw in a quasar to fit the blue part. And again, you get kind of the similar constraint because it's the same blue quasar. Maybe in this case, it's just piercing through the dust of the galaxy and emerging. So you have a massive, supermassive black hole growing very fast inside this also very massive galaxy. So what's the answer? We still don't know. Again, we can try to go redder here or deeper with the spectroscopy, maybe probe the continuum, see the absorption lines from the galaxy. But from the data at hand, we do not know. All right. So implications, again, right, so these are number densities for galaxies as a function of redshift. If some of these galaxies, these are different estimations, getting modeling the SED with different codes. Some of them are going to be above masses of 10 to the 10, so the number density compared to the models and predictions from pre-JWST data makes this population way too abundant, like a factor of 10. And if some of them are more massive than 10 to the 10.5, then it will be like a factor of 60. So the problem for these galaxies is that only a handful of them are overly massive. The rest are around 10 to the 10, but it's concerning compared to the number densities that we had before. Still no problems for cosmology because you can still reproduce this with different efficiencies in the halo. But again, the numbers are way too high. If they are AGNs, supposedly it's fine because these are the MUVs that you get. But remember, this UV luminosity, if you're modeling this with a scatter component, is from the scatter component, right? If you want to know the intrinsic UV luminosity of the bright red quasar, you have to correct for the dust of the red bright quasar that has a luminosity of 10 to the 45, 46, and then the intrinsic UV brightness will be somewhere here, right? So it will be like 2 orders of magnitude more than the faint end of the bright blue quasars. Still fine with them because it's around the number density of X-ray detected galaxies, and there seem to be a population of galaxies with broad lines that is emerging. Not all of them look like this, but certainly a lot more than what would we infer, right? These are galaxies, these are AGNs, so a lot more than what we expected before. And so I think almost done. So I'm just going to go quickly over the summary. I'm not going to read everything, just give you the key ideas. These objects are very numerous, and we still don't know what they are, but they are very easy to find, so I encourage every one of you to find these objects in your favorite surveys, use your color magnitude diagram, find them, try to model them. They all have these very characteristic blue and red SEDs. And this selection gives you only this kind of object. It's not mixed with other type of galaxies. It's just these weird blue and red galaxies. You find them, you try to model them. If we can get additional data in the mid-infrared, we could probably do a better job trying to figure out what they are. They are all compact and unresolved, which suggests the QSO nature. It may be favored, that maybe so only for one of the 2 components. And again, the SED modeling doesn't tell us anything yet, but it has different implications, right? If they're massive galaxies, even if they're not overly massive, they're still way more abundant than what we thought before. If they are relatively bright quasars, because again, they're very obscure, they're still 2 orders of magnitude more than the faint end of the blue QSO. So,
thank you. Are there any questions?
Thanks so much. This is a great summary of the conundrum we have, right, of the galaxy, quasar, composite issue. So, I guess the one thing I would ask about is the galaxy situation, and maybe suggest that it can't be counted out entirely, partially due to the volume density estimate. That you would have to produce 2 orders of magnitude more QSOs to come up with the, this population if they were all QSOs, and it may be not such a huge jump for galaxy-dominated emission. I know the one source that Hollis looked at in his paper, the UV emission where you see the UV excess. It's a little hard. I think you could, even though it is unresolved, there's perhaps a tiny spatial offset. So I'm wondering, what can you do other than just get spectroscopy for all of these in the rest frame UV that you would think that we could iterate on to solve the blue component? What dominates the blue component?
Yeah. Thank you. And again, you made that comment when we were looking at this galaxy, and I agree with you. There are some galaxies where you can get some UV escaping. It's just that it's weird for all these galaxies, especially if you go all the way to the selection diagram, right, where all of them, I don't have the color, right, but it's all of them. It's not just a little bit of blue. It's just they seem to be away from the other ones. They are so weird. And again, I forgot to mention, but that galaxy over there, that's the Zavala object. So that's a proper, really dusty galaxy, Redshift 5, infrared detection, but doesn't have these UV. So it seems to be different than the others. And as far as what can we do, again, I think that getting the MIRI observations can really make a difference if you can distinguish between the stellar bump, right, the SED should flatten, right? It's continuously rising with the data that we have. It continues to rise, but it should flatten eventually, or not. And if it doesn't flatten, then good for us because they will be booming in the other MIRI bands. We should pick them up very easily. If we could get a spectroscopy, and some people having a spectroscopy, if was having a spectroscopy, if we could go deep enough to see the stellar lines in some of these galaxies, then that would be confirmation that there is a stellar continuum. And of course, we would like to get the UV, but yeah, this, I have it here, yeah, it's magnitude 28, so the rest from UV is going to be tough. I think it's worth it, right? If we can go there and get it. I think there's some Grissom spectra, Danco, I think. I don't have it here, but maybe you know this paper. You've been in many other conferences where they have a Grissom spectra, and I think they pick up some of the UV emission looks from the quasar, but again, some of them may be quasars, some of them are not as extreme, so maybe they are toned down versions. Do we have a stellar continuum or not? I'd love to know, but yeah.
Thank you, Guillermo. I was wondering whether there's any benefits for stacking a bunch of your objects so that you could see whether there's actually an underlying, more extended, let's say, red component that comes from a galaxy that you could still get the PSF-looking signatures, but you could detect something beyond that.
So I don't have it here. I was going to mention that the other paper led by, I forget the name, I have it on the slide, a student at Yale with Peter Van Dokkum, they actually some of these galaxies like high-resolution image, and some of the brightest actually have neighbors. So maybe it's not the galaxy itself that is extended, but some of them may be actually brighter than the others. Remember that the median, I have that in the summary, right? The median is around magnitude 26, but some of them are all the way to 23 and 24. Some of them are really like 2 orders of magnitude brighter. It's the same kind of L-shaped scale up, and some of these actually seem to have like neighbors around. So maybe something is fueling whatever this is in a general galaxy. But they seem to have some things around, and then some of them I think they model with more than one component. So it's not clear whether it's associated or just nearby. But it seems like the ones that are very bright, it's for a reason. There's something else is happening around them. So maybe stacking the brightest one and try to figure out whether there's something around is the way to go.
Okay, another question here.
Yeah, very interesting stuff. So if I'm going back to Dale's scenario of the sort of patchy, escape of the blue light around the AGN, I might expect that the bolometric component in the blue part to the bolometric luminosity in the red part might show a large scatter because, it really depends on the stochasticity of the. Have you computed that? And is that like, it seems very consistent to me when I see these fits. It always seems like it's right around 1 or 2%, which seems weird.
These are multiple fits of the same galaxy, but you see that on Evo's paper as well, where this is the scatter fraction, and I think Dale said something of the order of 3% to 5%. So if this is 3, then 5 is here, then 10 is there, 20. So we see other versions of these galaxies where the L is actually like this part of the L is shifted up. So we see a range. I'm not sure we see a continuum, so that is like a smooth distribution. But they're not exactly all like that. Some of them actually have the blue, or the rest frame UV is slightly lower than the others. Some of them are more UV luminous, so to speak. So that might be evidence for that. But yeah, we'll need a larger sample to look into that.
Okay, thank you very much, Guillermo.